Good morning, one and all. Today, we are going to see a problem on economic load dispatch. Two generating units is given. Take down this problem. A constant load of 300 megawatt is supplied by two 200 megawatt generators, 1 and 2, for which the respective incremental fuel costs are given. So incremental fuel costs are given, that is DC1 divided by DPG1 is equal to 0.1 PG1 plus 20. Next, DC2 divided by DPG2 is equal to 0.12 PG2 plus 15 with the powers PG in megawatt and the cost in rupees per hour. Determine first what they are asking, most economical division of the load between the generators. Second, they are asking savings in rupees per day, thereby obtained compared to the equal load sharing between the machines. So this is the question given. So you need to understand the questions clearly. What they ask, first they ask most economical division between the generator, that is PG1 and PG2, that you need to calculate. Next they are asking savings in rupees per day. Here it is in rupees per hour. They are asking in rupees per day, thereby obtained compared to the equal load sharing between the machine. They are telling like by taking equal load sharing between the machines, you need to calculate the savings. That also they have given. So like this question, they may ask in 10-mark question. Now, this is the incremental fuel cost they have given in the problem. So what is the optimality condition? That is DC1 divided by DPG1 is equal to DC2 divided by DPG2 is equal to lambda. Here, whatever it may, some problems they may given as C1, some problems they have given as F1. So whatever the fuel cost, some problems they have given as cost like that. So whatever the notations they will give, so there is the optimality condition. So what we need to do, we need to equate this DC1 divided by DPG1 to lambda. So if you are equating this to lambda, you can easily find out PG1. So PG1 is equal to lambda minus 20 divided by 0.1. That equation you take it as 1. Similarly, we are equating second incremental fuel cost to the lambda, that is 0.12 PG2 plus 15 is equal to lambda. So from this easily you can find out PG2. So PG2 is equal to lambda minus 15 divided by 0.12. Take this as equation number 2. What is given in the problem? Demand. Demand is given as 300 megawatt. That is a constant load of 300 megawatt is supplied by two 200 megawatt generator. So 300 megawatt is the demand. Like this also they will give like a constant load 300 megawatt is supplied by two 200 megawatt generator. Generator size they are giving. So this data now just for confusing you. Okay, just 200 megawatt generators, that also they are giving. So you don't confuse between what is load and demand. So constant load of 300. So this is the demand or load or demand is 300 megawatt. So given in the problem, the demand as 300 megawatt. So PG1 plus PG2 is equal to 300 megawatt. Now what we need to do is we are substituting PG1 and PG2 in equation number 3. Take this as equation number 3. Substitute 1 and 2 and 3. That is PG1 and PG2 in 3. And from that we are calculating lambda. So we are substituted. Take your scientific calculator. Calculate it. Simplify it. We are getting the answer as lambda is equal to 34.0909. So you just tell in comment whether you're getting the same answer or not. So we are getting lambda is equal to 34.0909. Now from this lambda, you just substitute to the equation 1 and 2. Easily you will get PG1 and PG2. Just what we are doing is we are substituting in the PG1. PG1, take your scientific calculator, simplify it. We are getting the answer as 140.909 megawatt. Similarly, PG2 also lambda we are substitute lambda minus BI divided by 2A. So lambda minus B2 divided by 2A2. So here simply we are substituting and we are getting the answer as 159.0908 megawatt. So here PG1 and PG2 satisfying the demand, that is 300 megawatt. 300 megawatt it is satisfying, approximately equal to That is approximately we are getting the answer as 299.9998 megawatt. That is approximately equal to 300 megawatt. So it is satisfying the demand. Now, so the most economical division of the load between the generators are PG1 is equal to 140.909 megawatt. Next, PG2 is equal to 159.0908 megawatt. Now, what is as this is the most economical division of the load between the generators. So we calculate. What is the second part they have calculated? As the second part they have asked is savings in rupees per day, thereby obtained compared to the equal load sharing between the machines. Like that they have given. So they are asking for the savings. So savings in rupees per hour they are asking. So what is given in the problem? Incremental fuel cost DC1 divided by DPG1 is equal to 0.1 PG1 plus 20. So from this, you can easily calculate C1. So here differentiation you need to remove means you need to integrate. So C1 is equal to integration of 140.9. So 140.9 is here, whatever the answer we got. And what they said for a savings now, it is equally shared. The load is equally shared like that. One point is given. Here they have given is the savings in a day, thereby obtained compared to equal load sharing between the machines. So what is the demand is 300 megawatt. So equal load sharing between the machines are given in the problem. So we have to take as 150 megawatt and 150 megawatt. PG1 as 150 megawatt and PG2 as 150 megawatt here. So here what we are doing is we are integrating with respect to whatever the answer we got here. That is 140.909 and load is shared equally like that they said. No, so 150 megawatt. So 300 divided by 2 is 150 megawatt. So PG1 is 150 megawatt here. So from 140.9 to 150 megawatt, we need to integrate. So this we are substituting it 0.1 PG1 plus 20 into DPG1. So here we are differentiating with respect to DPG1. So here if you differentiate, you'll get 0.1 PG1 squared divided by 2 plus 20 PG1. While substituting the values from 140.9, that is lower limit is 140.9, upper limit is 150. So here you know how to, while integrating, you need to substitute over here. This 150 you need to substitute for PG1 first, and after that minus 140.9 you need to substitute this. So here we are substituting 0.1 divided by 2 is 0.05. Here PG1 we are substituting first as 150 megawatt. So 150 squared plus 20 into 150 minus the same thing here. This value you need to substitute, that is 140.9 we need to substitute. So similarly 0.05 into 140.9 squared plus 20 into 140.9. Take your scientific calculator, simplify it. We are getting the answer, that is cost answer as 314.3595 rupees per hour. Is the cost one we are getting. So as I said before, it is not only rupees per hour, even in dollars per hour, euros per hour, whatever the dollars. So who are watching this video, whatever your country currency, that currency they will give you some values. So it's the same thing you can solve. Not only rupees, not only dollars, not only euros, not only yen, like that, whatever the currency it might be. So you can easily calculate the cost. So C1 cost as 314.3595 rupees per hour. Similarly, we need to calculate C2. So DC2 divided by DPG2 is equal to 0.12 PG2 plus 15. Here what we are doing is here we want only C2, so we are integrating. So C2 is equal to integration of 159.09. 159.09 how we got is here PG2 value we got as 159.0908. So 159.09 we got here. So just substitute here the lower value. Here 150 how 150 how means PG1 and PG2 as equally sharing the load. So we just divided by 2, that is 300 megawatt divided by 2 is 150 megawatt. So PG2 is 150 megawatt here. So here what we are doing is we are integrating this with respect to DPG2. While integrating, you'll get 0.12 PG2 square divided by 2 plus 15 PG2. While taking lower limit as 159.09, upper limit as 150. Just substitute here and you can get the answer as minus 304.9276 rupees per hour. This is the cost 2 we are getting. Cost 2 we are getting as minus 304.9276 rupees per hour. Like if you take this as a 150, actually usually 150 should be the lower limit. While integrating, lower limit should be down. So if you integrate this minus sign will not come. That's all. So here we are getting as 304.9276 rupees per hour. Here I have taken as per whatever we got. But general rule for integration is you need to take a lower limit in the downside and upper limit in the this side. So this minus you can avoid. So here, but in the problem, what we got in the problem is we got 159.09 and 150 by sharing the load. So here we are getting minus 304.9276. So as it is, we are taking. So C2 is minus 304.9276 rupees per hour. So what they are asking is net savings. They are asking net savings. They are asking C1 minus C2. So C1, what is the value we got? C1 we got it as 314.3595 rupees per hour. C2 is minus 304.9276. So minus, as I said, minus you can neglect because here if you take this as a minimum value, this as a upper value. So if you substitute, you'll get positive cost. So here, if you minus this C1 minus C2, you'll get to the net savings as 9.4319 rupees per megawatt hour. Sorry, rupees per hour. Rupees per hour we are getting. So what they are asked in the problem is rupees per day. Per day they are asking. So rupees per day means into 24 you need to multiply. So whatever the value we got in rupees per hour into 24 hours in a day. So 9.4391 into 24, you'll get the net savings as 226.3656 rupees per day. This is the net savings we got for the whatever the asked in the problem. As I said, here you can use any thing because not only rupees, you can use dollars, euros, or whatever the currencies from your country that is mentioning here, you can take here because country to country, this data will vary and fuel cost coefficients also vary, depends on the load and the fuel cost coefficient and the savings also it will, and based on the coal rate also, this cost will vary by the country within the country to country, this currency will vary. So this is the net savings we got in our problem, that is 226.3656. Thank you.